The simplest type of wave phenomena to understand for light is actually two-slit interference or double-slit interference. And again, in this case, we're going to have two slits. They need to be very thin. And so we're frequently going to think of these as being less than 1 millimeter wide. And in different units, this is going to be equal to 100 microns wide. So this is still much larger than the wavelength of light itself, but it's still pretty small. So these are still really small, but bigger than the wavelength of light. Now the separation needs to be larger than the width. And we're still not going to make the separation of these meters, but in this case, half a millimeter. So this is the scale that you're typically going to see. You might see the width getting a little smaller. You might see the separation getting a little bit larger or a little bit smaller. But if you have them really close together compared to their width, you actually are going to see something that looks more like a single slit experiment. So this is the guidelines here. Now both slits are lit by the same laser beam. This means that your source has the same wavelength and there's no phase difference between your two slits. So that's important for thinking about the math leading to our interference. Typically we say that our screen is very far away, and so this might actually be 1 to 5 meters. So think about that length scale here. And that's to just really see this pattern clearly. We could bring the screen really, really close, but it's actually going to be hard for our eyes to see the spacing. So making it far away is just like magnifying the effect in a way. There is going to be a simplification in our math that does kind of depend on it being pretty far away. Lastly, again, we're really talking about a one-dimensional pattern here, that you can see that this picture is three-dimensional. We have this initial screen with the slits in it that is parallel, so it's kind of oriented vertically with respect to the viewing screen. But really at the end of the day, all we care about is this horizontal dimension here, and when we plot this, we're going to be thinking about what's happening in one dimension there. So this is a three-dimensional problem, but when we go to actually look at the fringes, we're really just looking at a one-dimensional problem. What we talk about when we talk about this pattern that we see, we call them fringes or interference fringes. I don't quite know the origin of the term. I might call them bright spots and dark spots, but fringes, spots, it all kind of just means the same thing. So we see bright spots and we see dark spots. So the bright spots are going to correspond to our constructive interference, which were our antinodal lines. The dark spots are where there's destructive interference. Again, remember that we have light coming in, and when here we say it's a plane wave, we can just think about this as like a really big laser beam compared to the separation between these. So remember that because we have these two sources, we're going to have those spots of constructive and destructive interference. So what you might have a little bit difficulty of seeing is that these points here are right where those circles are hitting each other. So if you always have this line corresponding to the intersection point of the circles, those are your antinodal lines. Those are your points of constructive interference. So once that gets to the screen, you have this bright spot. So one other piece of terminology that's really important is to know what we mean when we talk about the central one. So the central maximum is the one that is basically straight forward from the middle point between these two. So it doesn't necessarily align with either slit, it aligns with the point in between them. And remember that this isn't to scale, that again this distance here might be say half a millimeter, and remember that this distance here might be 5 meters, so actually once we're over here we might be talking about 1 centimeter. So please remember this picture isn't actually to scale. But the central maximum is going to be the point right in between. And it should make sense to you that there is constructive interference here because every point on this line is actually the same distance from each slit. So if you say, what is the path length difference along this line? Well, it's 0. So you get constructive interference because 0 times wavelength is a point of constructive interference. So you have constructive interference here because your wave is overlapping, and then there's going to be a dark spot, and then constructive interference again. So in the next video, we'll try to do out some of that math in great detail, but ideally right here, you should be able to connect what we discussed before about two-dimensional interference to these antinodal lines, and to see how if we then put our screen down intersecting this two-dimensional spatial pattern, we get this one-dimensional pattern. Now, if you're asking the question, why are these darker than these, that's actually something we're going to get to at the very end of this section of video. So for now, just focus on some bright spots, some dark spots, and then the variation in brightness is something that's actually depends on us understanding a different aspect of this phenomena.